Welcome to the next video on magnetism. In last video we finished off discussing that if there is a closed current carrying loop which is placed inside a magnetic field, then that suppose the magnetic field we discussed was coming outside the screen of your computer, and we experienced we discussed that if this closed loop current carrying loop is placed in a magnetic field, it will experience a torque. Now why it will experience a torque we discussed in the last class, but because it is a little bit difficult topic, it warrants an extra discussion on the same. So suppose I just wanted to again discuss why it will experience a torque. So suppose this wire carrying current loop is exactly in the plane of your computer screen, and the magnetic field is coming exactly out of your screen. Then the magnetic field and this area will make a 90 degree with each other, and the normal to this area or the area vector is defined by the normal to this area. So the direction of the normal to this area will be the direction of the area vector. We'll discuss in more detail shortly how to decide the direction of the area vector, but for now, if we work out that the force on any current carrying wire is IL cross B, and from the right hand thumb rule which we discussed in the last video, if we work out the direction of the forces, it will be as shown in the figure here. So if I just take a cross section, suppose I am looking to there is an imaginary green line joining the forces F and this force F. I have drawn an imaginary green line, and if I look it from this side, okay, then it will look like the imaginary green line will look like this, somewhat like this, and the forces will look somewhat like this force and this force. So if you notice that these forces pass through each other, so they will not give any torque to these forces will not create any torque, because if I extend this force and if I extend this force, they will pass right through each other. But imagine a case where I rotate this square loop about an axis which is given by the blue line. Okay, so I give a rotation theta about this blue line. After rotation about this blue line, a view if you can imagine, then it will look something like this, theta. And again if I look from here the green line, then now the green line is being tilted with an angle of theta with the horizontal. So now if we look at the forces which is acting on this and this, because this is now has gone up because I have given a rotation theta, and this has gone down, so there will be a angle theta between this wire green line with the horizontal. And now the forces, if I extend those forces, suppose I extend this force right through here, now it is not passing through F, but now I can drop a perpendicular from this force F to the extension line of the second force, this force which is the blue line, and now there is some perpendicular distance. So if we notice, we studied that if this is d, then this perpendicular distance will be d sine theta. And we had derived, I will not derive again, that because of this displacement now there will be a torque on this wire, and that total torque on this loop, if it has multiple loops, say 4 or 5 loops, then the total torque on this loop, current carrying loop, will be NI A cross V, where A is the area vector and B is the magnetic field vector. So the direction of magnetic field vector, there is no doubt. What will be the direction of the magnetic field? It is what will be given. If somebody gives the direction of magnetic field is coming out of the screen, like in this case, it is easy to find the magnetic field direction. What I also wanted to discuss is how to find the direction of the area vector. Now, any area, the area vector is defined by is a vector whose magnitude is equal to the area of this square loop. The magnitude of the area vector is equal to the magnitude of the area of this square loop, and direction is along the normal. So a unit direction is along the normal. So normal to this area is a line which is either coming out of your screen or going inside the screen. So there are two possible normal direction. One is which is coming out of the screen and one which is going inside the screen. Now which one of it is actually the direction of area vector? Is the area vector the normal which is coming out, or is the area vector the normal which is going in? So to show that, because I am very poor at drawing figures, again we use the right hand thumb rule to find out the area vector, but because I am very poor at drawing figures, I did some Google image search to find if there is any image which I can find to depict. So again here is an area, and here again current is flowing in this loop, and again the direction of normal, there can be two normal, one may be along this arrow or another can be opposite to the direction of arrow. So which one is it? The direction, whether it is coming out or going inside, is given by the again right hand thumb rule. The only difference here is now you have to curl your fingers. See, he is curling his fingers along the direction of motion of along the current direction. So here current is flowing in anti-clockwise direction. So current is flowing in anti-clockwise direction. So you have to try and curl your fingers in the same direction as the direction of current. So he is also curling his fingers along anti-clockwise direction. So in order to curl his fingers in anti-clockwise direction, the position of hand should be as shown in the figure, and in this case, if we want to curl the finger along anti-clockwise direction, the thumb should point in this, like the thumb should point outwards. Okay, but so this is the direction of normal, the direction in which your thumb will point if you want to curl your fingers along the direction of the current. So let's the case of two. So now only two cases will be there. One is anti-clockwise, like the case here, and the clockwise. So only two possible directions of current are there. So only two possible direction of area is there. So when it is anti-clockwise direction, as shown here, it will be always be coming out, and when it will be clockwise direction, suppose the current was clockwise, then if you could imagine, then to curl your fingers towards clockwise direction, your thumb should be facing the opposite direction. Okay, so if had it been clockwise direction, the area, your fingers would have curled in the clockwise direction, and if you wanted to curl your finger in the clockwise direction, your thumb would be pointing inward in that case. So your direction to the normal, if the current is in clockwise direction, the direction of area vector would be inside, going inside. So whenever the direction of current is anti-clockwise, the area vector will be coming out, and whenever the direction of current is clockwise, the area vector will be going in. Okay, so this completes our discussion on what effects magnetic field produce on different type of bodies like charged bodies in motion or current carrying wire. Now we will discuss how can we produce magnetic field. So one way of producing a magnetic field is to use magnets. Take a magnet which have a north pole and south pole, but here we'll study magnets in detail in some future videos, but today what we will discuss is how magnetism can be produced by a current carrying wire. So whenever there is a wire which is carrying current, say this is a wire which is carrying current, and I have this wire produces a magnetic field, and so let me study a very small length of the wire dl. So this small length of wire dl will produce a magnetic field in a region, in the nearby region. So let us study what is the magnitude of the current which this small length of wire dl, which is carrying a current I, produces at a point P, which is so the position vector of P with respect to dl is given by r. So let us find out what is the magnitude of the magnetic field produced by this small wire dl at a distance r, at a point P which is at a distance r from this wire dl. So the magnitude of this is given by the Biot-Savart's law. Biot-Savart's law gives us the equation for magnitude of the magnetic field which this wire dl produces. So because I am taking a small wire dl, the small magnetic field produced by this small wire dl will be equal to, as per Biot-Savart's law, 1 by 4 pi epsilon naught c squared. C is the speed of light, epsilon naught is the standard epsilon naught from our electrostatics, I. So it is the magnitude of current or magnetic field is directly proportional to I, dl for dl vector cross r vector by r cube. So again, generally 1 by epsilon naught pi square, 1 by epsilon naught c squared, epsilon naught c squared is taken to be, is defined as, because mu naught is also constant and speed of light is also a universal constant. So generally 1 by mu naught c squared, both are constant, so it is taken to be another constant mu naught, which is called the magnetic permeability. So if I replace 1 by epsilon naught c squared by mu naught, I will get mu naught by 4 pi dB is equal to mu naught by 4 pi I, same thing, dl cross r by r cubed. So this is called the Biot-Savart's law, and the value of this mu naught is 4 pi into 10 to the power minus 7, and the magnetic the unit of magnetic field is Tesla. So the unit of magnetic field SI unit is Tesla. Okay, 4 pi doesn't have any unit. I have a unit of ampere, and dl has a unit of meter, r has a meter, and r cube has a unit of meter cube. If I work out the unit of mu naught, considering that the unit of magnetic field is called Tesla, it will be Tesla. So R meter square, meter into meter is meter squared by meter cube will be 1 by meter, which will go at this side as into meter. So Tesla meter divide, I will come down in this side of the equation, by ampere. So this will be the unit of magnetic permeability, mu naught, and this mu naught, the value which I have given you, 4 pi into 10 to the power minus 7, and it is called it is the permeability of the vacuum. If I have perfect vacuum, then the magnetic permeability of vacuum is mu naught, and the value of mu naught or the magnetic permeability of vacuum is 4 pi into 10 to the power minus 7. So this is in terms of vector notation. So what will be the magnitude? So the magnitude of dB will be equal to mu naught by 4 pi, I will not write this again, dl into r, dl in cross r will be dl into r into sine of the angle of dl and r, divided by r cubed. So r cube will become squared if I cancel with the numerator r. So this, the magnitude of the magnetic field due to a small length of current carrying wire, the small magnetic field due to a small current carrying wire dl will be equal to mu naught by 4 pi I, this dl cross r by I cube becomes I dl by r squared sin theta. So this is one formula which we will use again and again. Will generally will not require the vector form of the Biot-Savart law, but the magnitude of dB which will be used to derive the magnetic field due to some known cases or some useful cases, again and again we will be using the magnitude of magnetic field is equal to mu naught by 4 pi I dl sin theta by r squared. So let us again now quickly use this Biot-Savart's law to derive some very known cases. One case is to, like, suppose I have a general current carrying wire of some length, and I want to find the magnetic field at a general point, say, which is at a distance of some distance d. So this distance is d at this point P, which is at a distance d, perpendicular distance d, and general case, let me join these ends of the wire from here to here. Suppose let me say that this makes an angle of, this side makes an angle of theta 1 and this side makes an angle of theta 2. So this is a very general case of any point with any point can be defined in the region, can be defined by these three parameters d, theta 1 and theta 2. This will also define the length of this wire. So if you are just given these parameters, what is the value of d, then I can work out what is the length of the wire and what is the point here. So this is a general case, and let us find out in this case, if this wire is carrying a current I, say in this direction, then what is the magnitude of magnitude of the magnetic field. We will discuss after some time how we can find the direction of the magnetic field, but for now let us focus on the discussion of how to find the magnitude. So from Biot-Savart's law, the magnitude, suppose let me take a very small element here. let me take a small element here. So this is a small element of length, say dl, which is at a distance of, this small element is at a distance of L from the point where the perpendicular is drawn, and this, suppose I say that I will compute this value, but this, suppose it makes an angle of theta. Okay. So now, using Biot-Savart's law, the magnitude of dV will be equal to mu naught, we just discussed, mu naught by 4 pi I dl sin theta. This is the r vector, and r makes dl, by the way, yes, I forgot, the dl vector, the direction of dl vector is given, is given along the direction of current. So magnitude of dl vector is the length of the wire, small length of the wire, and the direction of dl is the direction of the current. So the magnitude of the magnetic field will be given by the Biot-Savart law, which is mu naught by 4 pi into I dl sin theta, and this is because of the small length dl. And let us find out some relationship between what is the length, what will be the relationship between L and theta. Okay. So if I just use some simple trigonometry, if this is theta, this will be equal to 180 degree minus theta, this angle, the inside. Okay. So this angle will be 180 degree minus theta, and if this is L, then we know that this is D, and the relationship between L and D is L by D. If this is theta, L by D will be equal to cot of, from this right angle triangle, cot of this angle, which is 180 degree minus theta, 180 degree minus theta, and cot of 180 degree minus theta we know is minus cot theta. So we will get L will be equal to minus D cot theta. And if I differentiate both sides of this equation, what I will get, because we are not changing D is constant, so dl will be equal to, D will come out of the differentiation sign, minus D, and the differentiation of cot theta, if you remember, is minus cosec square theta. So minus cosec square theta and this minus sign will cancel out, and it will become plus sign, and this will become cosec square theta d theta. So I can just substitute this value of dl, which what I have got, into this equation. So dB will be equal to mu naught by 4 pi I into D into cosec square theta d theta. And sorry, I missed another important term. So Biot-Savart's law is I dl sin theta by r squared. Okay. So again another relationship, what will be the relationship between r and theta, r d and theta? So we know that if this is theta, r will be the hypotenuse, d is the let me write it here. So sine of 180 degree minus theta, sine of 180 degree minus theta will be equal to d by r. So r will be equal to d, d goes here, r goes here, and so d by sine theta, we know sine of 180 degree minus theta is sine theta itself, d by sine theta, and d by sine theta is cosec theta. cosec theta. Okay. So let us replace the value of r in the Biot-Savart's law. So r is equal to d cosec theta. So this is divided by r squared, so it will be d square cosec square theta. Now if this is d square cosec square theta, then this one thing which I have missed here is the sin theta here. So I need to put sin theta here. Now I will cancel. So this cosec square theta will be cancelled with this cosec square theta, and this will become dB will be equal to mu naught by 4 pi I d. D and d squared gets cancelled, so it will be just d and d squared will cancel. So I sin theta d theta by d squared. Sorry, only d. So this d squared is getting cancelled with this. So all I need to do now is just integrate this to find the total magnitude of magnetic field here, dB. I just need to integrate both sides, okay, and the limits will be b from b is equal to 0 to b, and theta will go from theta 1 to theta 2, because we are changing the value of theta from theta 1 to theta 2. So if I just integrate this from 0 to b and this from theta 1 to theta 2, this will become mu naught is a constant, 4 pi d is a constant, 4 pi d, integration from theta 1 to theta 2 sin theta d theta. And I know that integration of sin theta is minus cos theta, and if I just put the definite integrals, this b will come out to be mu naught, I missed the I here, there is a current also here, I, mu naught I by 4 pi d cos theta 1 minus cos theta 2. So this is a general case where there is an arbitrary length of the wire and which makes an angle theta 1 and theta 2 from our point of interest, and for that the magnetic field at any point P which makes an angle of theta 1 and theta 2 with the wire is given by, and at a distance d, the magnetic field will be given by mu naught I by 4 pi d cos theta 1 minus cos theta 2. Now let us do some general cases. First general case is, suppose this is an infinite wire, okay. If this is an infinite wire and I want to find the magnetic field at a point P which is at a distance d from the infinite wire, if this is an infinite wire, theta 1 will be 0 and theta 2 will tend to be, in a limit case, theta 1 will tend to be 0. If this very long, this wire is very long, then theta 1 will approximately equal to 0, and if this is very long, then theta 2 will tend to become 180 degree. Okay, if you can imagine that, if this wire, if I take this wire to infinity, then this line will tend to make an angle of 180 degree with this. So if that is the case, then if I just put cos 0 is 1 and cos 180 degree is minus 1. So 1 minus 1 will become 2. So if the wire is infinitely long, then the magnetic field because of an infinite wire will become mu naught I by 2 pi d. 2 pi d. Also another case we can find, an important case, what if this d is a perpendicular bisector, okay. What if this point is at the midpoint of this wire. So suppose the length of the wire, let me take it as a, okay. So this length is a. If this length is a and this point is at, this line is a perpendicular bisector, or that means this point will be a middle of that midpoint of this. So this length will be a by 2 and this length will be a by 2, okay. So let me erase some of the stuff for clarity. And so this will be a by 2, this side will be a by 2 and this side will be a by 2. So if this are a by 2, then what will be theta? If this is a by 2, this is d, then what will be cos theta 1? So cos theta 1 in that case, so let me do that here. Because this is no more required. Okay, so cos theta 1 is nothing but cos theta 1 will be base divided by this side. Okay, so this is, we know that this is a by 2, and this will be square root of this squared plus this squared. So this will be square root of a by 2 whole squared plus d squared. If I just simplify this, I will get cos theta 1 will be equal to a by square root of a squared plus 4d squared. Okay. So because this is at a perpendicular distance, this is a perpendicular bisector. If this is a perpendicular bisector, this will be a by 2, this will also be a by 2, and this will be theta by 2. This will also be theta 1. Okay, so this angle will be equal to this angle. So cos of this angle will also be equal to a by a squared plus 4 pi d squared. But the cos of theta 2, now theta 2 will be equal to 180 degree minus theta 1 if this is the perpendicular bisector. And we know that 180 degree minus theta 1 will be equal to minus of cos theta 1. So cos theta 2 will be equal to cos of 180 degree minus theta 1, because theta 2 will be 180 degree minus theta 1, which will be equal to minus cos theta 1, and cos theta 1 is this quantity. So cos theta 2 will be just this term, which is a by square root of a squared plus 4d squared with a negative sign. And if I just substitute the values of cos theta 1 and cos theta 2 in this generalized equation, then what I will get? B, if this point is at a perpendicular bisector and at a distance of d from the perpendicular bisector, then B will be equal to, if I just substitute the value of cos theta 1 and cos theta 2 and simplify that, I will get the final answer, which is mu naught I by 4 pi d times 2a, okay, because a minus minus a will become 2a divided by square root of a squared plus 4d squared. So these are the some special cases. One is what if the wire is infinite. This is a general case. This is a general case. You can use it for any value, and with this case you can deduce some special cases like what if the wire is infinite, or what if the point is at a, where I am finding the magnetic field, what if that point is at a perpendicular distance from the is at the perpendicular bisector of the wire. Next important thing which worth discussing is we have find the, I should not put a vector sign here, this is the magnitude of B. What is the direction of B? Okay, so again to find the direction of B, I did some Google search, and again here we have to use a right hand thumb rule. So suppose this is the current carrying wire. Okay, what is the direction of magnetic field? This is a good figure. The current direction is current is going top. So again we have to use a magnetic field, but now in this case our thumb will point towards the direction of current, and once it points towards the direction of current, then I will curl my finger. I will imagine that I am curling my finger around the wire. Okay, so now the direction of my curling of finger will give me the direction of the magnetic field. So see, so here in this current carrying wire will produce a magnetic field, circular magnetic fields. The magnetic field of lines will be circular, and circular can have two directions, either clockwise or anti-clockwise. So once I point my thumb towards the current carrying wire, whether the magnetic field is clockwise or anti-clockwise will be given by the direction of my curling of fingers. So if the current is going upward, my fingers will curl in an anti-clockwise direction. So this is the direction, see the arrow here. So this is the direction of the current, which is of the magnetic field, which will be anti-clockwise direction. Here is another example, another figure from simple Google image search. This is the direction of the current. My thumb is pointing towards the direction of current. My fingers are curling anti-clockwise direction. So the magnetic field around the wire will be in anti-clockwise direction. So here there are these magnetic fields. If I point my thumb along the wire, I have to curl my fingers in an anti-clockwise direction. So magnetic field around here is in anti-clockwise direction. So to the right of my wire, the magnetic field lines are going inside. So going inside the screen means I can denote this magnetic line by a cross, by a circle and a cross, and to the left of the wire I can denote the magnetic line for force, because it is coming towards us. I can denote by a circle and a dot. Similarly, let us find if there is a case where the magnetic field is the current. Yes, so here the current is going down. So now my thumb is pointing down. So if I want to curl my fingers around the wire while my thumb is pointing down, then I have to curl my fingers like this, which has to be in clockwise direction. So here in this case, if the current is flowing down, then the magnetic field around the wire will be in clockwise direction. So this is how to find the direction of magnetic field. So a circular line or a current carrying wire, which is a linear wire, it produces circular magnetic fields. So here is one good example. Here the current carrying wire is circular because the wire is going up, or the current is going up, it is producing magnetic fields in an anti-clockwise direction, and you see the magnetic lines of force which are circular in nature, magnetic field lines. So with this discussion we will end today's or this video. We'll see you in next video.